Hello, everyone. I'm Fernando Pereira, a professor in the Computer Science Department of the Federal University of Minas Gerais, and today we continue to see how the partnership between industry and academia contributes to bring innovation in design and development of compilers. In this last part of the presentation, I will try to talk a bit about our own experience with the industry while being part of a research lab in a public university, which is the Federal University of Minas Gerais in Brazil. Last time we saw that there is a very positive cycle of support between the industry and the academia. We saw some stories from Meta and from the LVM Foundation, for instance. Now I will try to show examples of this partnership in our local ecosystem. For those that don't know, UFMG is located in the city of Belo Horizonte, which is the capital of the state of Minas Gerais in Brazil. Belo Horizonte is a large city, perhaps the sixth largest in Brazil, with a population of almost 2.5 million. If we count the metropolitan area, we might have perhaps 6 million people living around there. UFMG is the largest university in Belo Horizonte. Well, that's one of the largest public universities in Brazil, as a matter of fact, with almost 45,000 students, out of which 15,000 more or less are graduate students. It's considered a good university in Brazil, and competition to get in computer science is very tough. Last year, the applicant to seat ratio for computer science at UFMG was 33.4 applicants per spot. And within UFMG, we have the Compilers Lab, where we do research on all aspects of compiler construction and design. The lab hosts master and PhD students from UFMG's graduate program in computer science. Many of these students have contributions that ended up becoming part of popular compilers such as SpiderMonkey, Mozilla Firefox, LVM, or Mesa 3D. As an example of such contributions, the implementation of Mesa's 3D divergence analysis is based on a technique that was invented in UFMG's Compilers Lab. This divergence analysis, which Mesa 3D uses, was designed more than 10 years ago by two grad students, Bruno Coutinho and Diogo Sampaio, when the lab was on its very beginning. At the time, we didn't even have a proper room. Much has improved since then. But now, I would like to talk about a different group of students. In the second semester of 2025, Cadence Design Systems hired 5 alumni from the lab to work on XNNC, which is a compiler that they use. 2 of these students were undergraduate research assistants, and the other 3 were graduate students. I would like to talk first about 2 of these graduate students, and I shall start with Michael Kanesh. Michael has a PhD in computer science. He got his PhD in 2024. His PhD program was fully sponsored by Cadence. While pursuing his PhD, Michael worked on techniques to improve tensor compilers. From this work resulted the code optimization algorithm that we call Droplet Search. This algorithm is described in the paper The Droplet Search Algorithm for Kernel Scheduling, which was published in ACM Transactions on Computer and Code Optimization in 2024. Droplet Search is a technique to optimize computational kernels. But what's this? What's a computational kernel? A kernel in a computational graph is a basic computational unit, such as a matrix multiplication, convolution, or activation function. And that processes input tensors to produce output tensors. As an example, the gray box shows an abstract representation of a kernel that performs the vector operation C plus A times B. There are compilers, such as TVM, for instance, that can translate a more or less abstract representation of a kernel, like we have within the gray box, into very optimized code that runs on CPUs, GPUs, or specialized tensor processors. But to perform this translation, the compiler must find a concrete representation for the kernel. For instance, we can represent the abstract kernel on the gray box as a nest of loops performing addition and multiplication of vectors. But notice that there are really many ways to implement a kernel. For instance, we could interchange the loops to obtain better cache locality. Or we could interchange and then tile the loops to keep more data in cache as much as possible. And if you do tiling, then we could vary the size of the tiling window, which could be 16 or 8 or any other value that makes sense. The art of such optimizations forms a whole branch of science within the domain of compilers, with many books written about it, like the classic book from Michael Booth in this figure. Implementing the optimizations correctly is difficult, and choosing the right parameters for these optimizations is even more difficult. Indeed, some optimizations like tiling are parameterized. In the case of tiling, the parameter is the size of the tiling window. These two kernels, for instance, represent different parameterizations of the same optimization, which is tiling. The universe of possible valid parameters for an optimization forms what we call the search space of that optimization. As an example, here we are showing two of these spaces. In this case, the x and y axes are the dimensions of the tiling window, and the z-axis is the performance of the kernel if we run it with that parameterization. Well, if we have the search space, an obvious question is how we can find the best configuration of parameters. That would give us the minimal point in the performance curve. Compilers usually solve this problem doing something called auto-tuning. That's basically a feedback system. We run the kernel, profile it for performance, and then use the observation to look for another kernel. TVM has lots of different ways to do auto-tuning. The simplest approach is just to sample random kernel configurations in hopes of finding the optimal one. Or else we could vary the parameters on a grid, which is more systematic than random search and avoid sampling the same kernel twice. Or we could try some more advanced techniques. TVM, for instance, uses a genetic algorithm to combine previous observations into new kernels that are likely to be efficient. What Droplet Search does is to use a hill climbing approach to try to approximate the optimal kernel configuration. In this sense, we can think about Droplet Search as a post-optimization phase. First, we find a search space, that is a configuration that gives us a kernel. Then we use the Droplet Search to adjust the parameters of that configuration. Nowadays, Droplet Search is part of the meta-schedule infrastructure. It's part of Apache TVM. So the meta-schedule uses different algorithms to obtain different kernel configurations. Imagine that each configuration represents a different interchange of loops, for instance. So Droplet Search samples these configurations, TVM samples these configurations a number of times using, for instance, an evolutionary algorithm or XGBoost, which is a machine learning technique. Then it chooses the best configuration that it found in the initial exploration phase. And finally, it uses Droplet Search to exploit this configuration via the coordinate descent algorithm. That is the essence of this approach. This algorithm was invented during Michael's PhD, who had a scholarship donated by Cadence. And now the algorithm is used in open source projects such as the TVM compiler, for instance. As a result of this work sponsored by the industry, Michael published different papers, and he could use the knowledge acquired doing this research to contribute back to the tools that are used within Cadence itself. Let me give an example of such a contribution. So let's forget for a while kernel tuning and look into another kernel-related optimization called kernel fusion. The current implementation of kernel fusion used by XNNC, which is a Cadence compiler, was invented by Michael during the final year of his PhD. This algorithm is used in a proprietary compiler, but was published in a public conference, which is the International Conference on Compiler Construction, that happened in Las Vegas on March of 2025. Kernel fusion is a very important algorithm used in tensor compilers. To understand why it's important, we must consider that tensor compilers see programs as a computational graph, where vertices are kernels and edges represent the flow of data in tensors between these kernels. For instance, here's an implementation of single-head attention, which sits at the core of the LLMs that we use nowadays. Some of these sequences of kernels could be combined into single operations. This is called fusion. Fusion has many benefits. It tends to avoid the creation of auxiliary buffers, for instance, improves data locality, and avoids unnecessary data transfers. On the negative side, it might increase the memory footprint of kernels. Essentially, kernel fusion is implemented as a classic compiler optimization called loop fusion. For instance, if we have this sequence of multiplication and addition of matrices, then we could combine the two outermost loops into a single nest of loops. If we can keep the three tensors A, B, and D within memory, then the fusion might be quite profitable. Once Michael finished his PhD, he was hired by Cadence to work on the development of XNC, which is, again, the compiler that converts deep learning models into the binary code that their DSPs use. Michael's first contribution was implementation of the new kernel fusion algorithm there. And from there, Cadence hired two more students, Guilherme and Vitor. In this way, they were creating a small team to maintain XNC. XNC is implemented in C++, and the last time I checked, it had 1.5 million lines of code. These boys were then working to make it compatible with MLIR. XNC is a neural network's computational graph. In these graphs, vertices are operators. We call these operators kernels. Typical kernels will implement the layers that we find in neural networks. And the edges in the graph represent the flow of data within the many kernels that form the neural network. So if we look into the code that XNC generates to implement a neural network, we can imagine that these kernels are function calls that invoke specialized library routines like conv2d and relu in this example. And we might also find some gluing code that implements the operations that we cannot decompose into pre-built kernels. This code will be eventually converted to a format that we can deploy into digital signal processors and other specialized hardware. Today, Cadence has 5 alumni from the Compilers Lab working on XNC. These students all have training in research and can contribute to innovate not only the implementation of XNC, but also the algorithms that it uses. Let me tell you the story of another of these boys, who also had its master fully funded by Cadence within the public university. That's João Amorim. He got his master degree on June of 2025 and now works at Cadence Brazil. I would like to talk a bit about his project as another example of cooperation between the industry and academia. During his master, João has designed and implemented a tool called ChiGen, which is a Verilog Fuzzer. In this work, he was helped by other students from UFMG, like Luisa Mello, for instance. ChiGen generates random Verilog designs to test EDA tools. Here's an example of the kind of design that ChiGen can generate. These random Verilog designs are meant to find bugs in EDA tools. ChiGen has been very successful in this regard. Here is a list of some bugs that it has discovered in different tools. All these tools are quite popular and enjoy the support of large communities of users. Bug 2233 is easy to explain. That's a situation where variables parser was accepting programs that did not have matching block delimiters. Here's another example of an invalid Verilog design that ended up causing a crash in variables parser. The problem was happening in a particular rule. Later on, Rafael Sumitani, who was a student in our lab, ended up producing a PR that fixed this issue that was accepted in variables parser. And here's a design that caused an infinite loop in Icarus. This tool, ChiGen, was implemented as part of a project sponsored by the industry in the university. It's totally open source, but it's used within Cadence. It was presented in the Cadence Innovation Conference in June of 2025 by Milene Crepald, who was the Cadence researcher responsible for coordinating the project. Right now, there are a number of people using ChiGen to stress test electronic design automation tools. And there are contributors from outside our group who participate in the project as well. As a result of this cooperation, we have published a number of academic papers. For instance, this one here describes the core technique that we use to produce Verilog designs. We generate programs using a probabilistic grammar and use type inference to ensure that designs are valid. You can know more about it reading the paper. ChiGen is trained with real Verilog designs. To train it, we have assembled what's perhaps the largest open source collection of Verilog benchmarks. These programs were mined from repositories that had permissible licenses. And these other papers describes the collection which we call ChiBench. This project, ChiGen, is an example of how the industry and the academia help each other, of course. From this cooperation between Cadence and UFMG, not only ChiGen came out, but also Droplet Search, which is now on Apache TVM. There were many high-skilled students who were able to obtain good education. Cadence has funded one full PhD program to master's students, to undergrad researchers, and the cooperation is still ongoing, so we can expect more students to benefit from it. And they really need this workforce. That's so much true that last year professionals from Cadence went to the university, to UFMG, and taught a course on hardware verification themselves. This was one of the first courses taught by professionals from the industry in the public university in Brazil. And this cooperation is fostering a more academic-oriented culture within the company itself. This year, Cadence engineers from the Belo Horizonte branch have published papers in conferences like CGO and the International Conference on Compiler Construction, for instance. But all this is just an instance of how much benefit comes from this cooperation, this partnership between the industry and the academia. This cooperation leads to the progress of a very healthy community where theory can become practical tools and education can be translated into high-value jobs. And with this last remark, I close this series of videos. I hope you have enjoyed them. And if you have questions or more nice examples of cooperation between the industry and the academia to foster innovation in compilers, please feel free to reach out to me. Thank you.